Now that we understand ER diagrams, the next step in the database design process is taking requirements and operationalizing them into an actual database. The purpose of drafting an ER diagram was effectively picking out the important information and reimagining it in such a way that it can be easily converted into a database format. So where the primary task for Chapter 2 was taking a list of text requirements and turning them into an ER diagram, think of the primary task of Chapter 3 of taking an ER diagram and turning it into a relational schema. In this class, we're going to deal exclusively with relational databases, which are made up of relations. Relations are special types of tables that are used in these databases and are distinct from more generic tables that you might find in, say, a spreadsheet. We'll talk about these rules in detail in a minute, but for now, let's suffice to say that these rules are going to dictate some of the structure of the database. Throughout this class, I'll use relation and table interchangeably. When I say table, assume I mean a table that conforms to the requirements of a relation. The terms that people use are going to vary somewhat, but let's look at a very simple example. This table reflects synonyms and is conceptually grouping a concept together. Each row represents the same concept across the whole row. So for example, an entity is a synonym for a relation, is a synonym for table. Each column represents a specific aspect of these synonyms, namely the terms a person in these job roles might use. The intersection of these represent a defined aspect of this concept, so say what a data scientist will call a table. Now, that said, relational databases have special rules which they must adhere to. They're summarized here, but let's go through these one by one. This is perhaps a trivial statement, but a relational database needs to be made up of relations. Not all databases are relational, but relational databases have been the de facto standard for going on 50 years, and presumably will be long into the future because they're robust and flexible for most purposes. Non-relational databases are typically well suited for one specific application, but practically unusable for any other application. The first true rule of a relation is that each column must be named and have a defined domain which is consistent throughout the column. Maybe putting this in a simpler way, each column needs to be describing something in one way and doing it the same way consistently. So if I were recording homework scores, I wouldn't mix numeric scores and text. Next is that each row needs to be unique in its entirety. Really, what we mean here is that if you have two identical rows, you just delete one of them. Perhaps the most important rule is that each cell is atomic, or that it can't be reduced any further than it currently is, at least according to the column definition. So if we define homework as an integer, we can't put two integers in there to represent multiple homeworks. We'd have to have separate columns. I'll refer to this as the atomicity requirement later. Finally, as far as a database is concerned, there is no true order to rows and columns. This is something that the database backend handles, so you can just assume that it's true. So what's the goal for this chapter? Ultimately, we're looking to draft a relational schema like the one above. This is a complete representation of the arrangement of the database, in contrast to the ER diagram, which is a restatement of the requirements. Unlike an ER diagram, we can use a relational schema to navigate the database as a map, both in the sense that we have the names of the tables and columns that we can use in SQL queries, but also because we'll see which columns link the tables together. So let's get started on this. The simplest component of an ER diagram to map onto a relational schema are entities. These will always become tables. Most of the time, attributes are connected to these tables become columns within the tables. There are some minor exceptions to this. For example, we would ignore composite attributes in the relational schema, but instead just include their components, and we'd have to mark optional attributes as optional in the relational schemas as well. Derived and multivalued attributes have to be handled separately, but we're going to get to those later. Unique attributes generically get marked as unique. That said, most of the time we're going to be dealing with ER diagrams that have exactly one unique attribute. Remember candidate keys? If we have more than one, we need to pick one, and it doesn't really matter which, as long as they're actual candidate keys, which is to say unique and non-optional, and declare that to be the primary key, which we're going to talk about in the next slide. All the other candidate keys will just get marked with a U for unique. So let's get back to the primary key, which has to meet the definition of a candidate key. That is, it's unique and it's not optional. Every table needs to have exactly one primary key, and even if a primary key is made up of more than one column, it's still only one primary key. Tables can be linked together because of these keys. We'll focus on the two types of keys here, primary and foreign keys. A primary key is a column or columns which is filled with unique values. In some cases, these numbers are auto-generated by just taking the row number. In other cases, they're tied to some data point that meets these requirements, such as a student ID in a school or taxpayer ID for interactions with the IRS. Importantly, the primary key must be unique and cannot ever be missing, which makes up the entity integrity constraint. Foreign keys are conceptually similar but play a different role. A foreign key is a primary key from another table, which defines the relationship between these two tables. Let's look at an example of this. Here we have a small ER diagram and some toy data. Now, note the department ID is in the employee table even though it's not an attribute in the ER diagram. That's because in this case, the department ID and employee is acting as a foreign key and pointing to the row in the department table with the equivalent primary key. As we'll see once we start writing SQL queries, we can use this linkage to return a list of employees in the departments or a list of managers and all their employees. Now let's walk through the process of converting an ER diagram into a relational schema. On the left, you'll see the ER diagram, and on the right, the resulting relational schema. Let's look at what each of these components represent. First, remember that all entities get mapped to tables. So we take the employee entity on the ER diagram and map it to an employee table on the relational schema, and similarly with department. Next, we take the attributes and map them onto columns. We only have one candidate key in each of these, so it automatically becomes the primary key. The other attributes are normal, and accordingly, we just insert them as normal columns. We'll discuss the process of actually making these a key in ERD Plus in class. The next part requires a bit of a discussion as to how we map relationships on relational models. One-to-M relationships are the most common and have a hard and fast decision rule. We always put the foreign key on the M side. In this case, the M side is employee because the many, crow's foot, indicator is attached to the employee entity. I'm going to use this nomenclature from here on out. When I reference the side, I mean the side that has the indicator attached to it, as opposed to the ER diagram reading of where the cardinality indicator opposite the entity is red. So when the foreign key goes on the M side, which is employee, conceptually, this makes sense because departments have many employees, and we couldn't have the employee list as a foreign key since we'd either need to have one column for each employee, which isn't ideal, not the least of which because we have an arbitrarily large number of employees, and we couldn't just put every employee in one cell because that would violate the admissivity requirement. But since each employee only has one department, we can just put the foreign key on the employee table. So ultimately, if we were to draw one-to-one comparisons from the ER diagram to the relational schema, it would look like this. One-to-one relationships are somewhat easier. You can put the foreign key on either side. It doesn't really matter which. That said, optional relationships add a small wrinkle to this. When a foreign key is on the opposite side from the optional marker, we need to mark that foreign key as optional itself. So if we put the foreign key in the student table on this slide, we would need to mark that foreign key as optional. Now, if only one side is optional, I recommend you put the foreign key on the optional side where you don't need to mark the foreign key as optional since it's on the same side. That said, it's perfectly legal to put the foreign key on the opposite side, you just need to mark it as optional. This is notable since if the one side of a one-to-M relationship is optional, you have no choice but to mark that foreign key as optional, since one side will be required to be opposite the foreign key because you always need to have that foreign key on the M side. The last thing we need to address are M-to-N relationships. This is a bit stickier. We can't put the foreign key opposite the M side, but because with M-to-N relationships, both sides are opposite the M side. So we'll have to do the next best thing, which is just make up a whole new table in the middle, and that way there are no opposite sides. Essentially, what we're doing here is creating a whole new table which will have one row for each instance of relationship between students and parents, and that row will have the foreign key for both. Remember that with M-to-N relationships, you can also have attributes which will handily go in that table. There are a couple things to keep in mind here. All tables still need a primary key, and in this case, the primary key is going to be the combination of both foreign keys. It is completely legal to have a foreign key also act as a primary key. The other thing is that we don't need to consider optional relationships at all when we deal with an end-to-end relationship. If we have, for some reason, a student with no parents in our database, that student just won't be represented in the related to table. This is handy for converting an ER diagram to a relational schema, but in the real world you might want to catch an error like that, which means you'd have to have some kind of separate check though. For this class, just don't worry about it. Remember that optional minimums and end-to-end relationships are already represented, and call it a day.